Good morning, students. Good morning, students. In today's class, we just start with what we have done in the previous class. Since we got a long break of nearly 25 days, right? 24, 25 days. So we just have a glance of what we studied in the previous class, right? So already you can just see the video also regarding this chapter, that is band theory of solids. But still, we'll have a very quick recapitulation of the topics what we have studied in the previous class. Then we'll move to the our main topic, right? So we just had the information regarding the band theory of solids. So you can just see this band theory of solids, right? So in the band theory of solid, what is actually the meaning of the band theory of solids, right? So here we, in the chapter unit 1, chapter 1 and 2, we had very clear idea regarding the crystal, how we can just proceed with the uh, three-dimensional structure of the crystal by studying it in two dimension. So we just considered some important parameters, and we move forward in the unit 2 regarding the uh, development of the free electron theory. Here, what is the meaning of free electron theory? So we are having a different approaches given by different scientists regarding the free electron theory. So, in the first section, we studied in the previous class also. So, we'll just have a very quick recapitulation of this free electron theory. So, the basic theory that we are dealing with, that is called classical free electron theory, which has been proposed by Jordan and Lawrence, and it's a macroscopic theory. So when we say macroscopic theory, it means that the we are talking about the uh, what you can say in general, right? So in which the electrons what is actually this macroscopic theory? So the macroscopic theory in which the electrons move freely in the um, lattice, and which is obeying the basic laws of the classical mechanics. And here we can just say that electrons moves in a constant potential. So what is this actually constant potential? You already had the information regarding the constant potential. It means that the electron will have its maximum energy at a particular instant, and then when it is colliding with the positive ion core, the energy will be reduced, and this part has been shown by different assumptions, schematic diagrams, and we also will see the schematic diagrams now. So we'll just move forward to this uh, basic theory, that is classical free electron theory. And there are this classical theory has been proposed in the year 1900, and which is also known as Drude and Lawrence theory. So there are important postulates. You already studied this. So according to them, they say that the atoms are composed of different your solids are composed of different atoms, and each atom will have the central portion is the nucleus around which the electrons are revolving, right? So according to Root and Lawrence, as they say that the electrons are free to move in all the possible direction in the metal. And when we say free electron, definitely I should obey the law of conservation of the classical kinetic theory of gases. That is, we just say classical kinetic theory of gases. When you say that the electrons are freely moving, so we just resemble the electron with the molecules of the gas, in which you already know that in gas state the molecules will move freely. So we can just say that the molecules of the gas have been compared with the electrons, and then the electrons are assumed to be moving freely in all the possible directions. And when I say all the possible directions, so it means that it will have some velocity, and that velocity can also be calculated by Maxwell-Boltzmann statistics. You can just say the classical free electrons in the metal is obeying the Maxwell-Boltzmann statistics. Here we are just dealing with the what is happening to the electron when it is moving in the metal. So we are interested in knowing this particular aspect because of its because of the various applications of this electron when it is moving in the metal. So these are the basic concepts that we have already studied in the last class, and what is happening when the electrons are colliding with each other. So that collision is neglected here. So here we just say that collision is neglected, and if the collision is occurring, then we just said that the collisions are elastic, and since it's an elastic, then definitely you'll not find any loss of energy. This is a very important aspect that we studied in the previous one, and definitely we'll have some merits and demerits of the classical free electron theory. So by means of this classical free electron theory, we also verified the Ohm's law, and the electrical and thermal conductivities of the metals have been explained by the classical free electron theory. So, what is actually the main drawback of classical free electron theory? So, the classical free electron theory says in detail about the electrons, and since you can see the electrons is not a macroscopic particle, but it is a microscopic particle or elementary particles. So, it's a microscopic theory. That is the important what you can say disadvantage or the drawback of classical free electron theory. So when we move to the next scientist, we already discussed that there is a scientist called Cronic and Penny, and they say that inside the crystal, the what you can say the electron movement will be looking in this particular. You can see this particular schematic diagram in which the electron will move in a particular square wells. We can say they are moving in square wells. So we just say that is called array of square wells, and this can be explained mathematically by using the Schrodinger wave equation. Right? That will deal with the next unit. What is actually Schrodinger wave equation? What is actually the psi function? And what is actually the importance of the Schrodinger wave equation? And what is the importance of psi also? We just discussed in uh, the latest section regarding this, right? So here we just start with the important aspect of the what you can say the Chronic and Penny model, in which it say that the Chronic and Penny says that the electrons will move in the form of a square, right? So you can just see this 0 plus a to a and 0 minus a minus 2a. So now this should be verified mathematically. So what the Chronic and Penny has been considered that by taking the help of Schrodinger wave equation, uh, right, in a one-dimensional periodic potential. So they solved some mathematical equations, and they had a very good conclusion regarding the movement of the electron when it is moving from different limits. We just see that, right? So since the Schrodinger wave equation is a second order differential equation, that is O square psi by dou x square plus 8 pi square m by h bar square into e minus v into psi is equal to 0. Now this is actually the Schrodinger wave equation, and since it's a second order differential equation, it should have the solution that is called psi of x is equal to uk of x. You can just see the figure. This symmetrically psi of x is equal to uk of x exponential of ikx, and here here we have the scientists have introduced some function. That function is known as block function. So uk of x can also be written as uk of x. So say since the electron is moving inside the crystal, it will take the periodicity of the crystal. It will take some important character, and that character has been indicated with the letter small a, which is called lattice constant of the crystal. And when we just solve this particular solution, the possible energy equation, what we get is nothing but cos k is equal to p sine alpha a by alpha a plus cos alpha a. Now this is actually the, what you can say, the solution after different calculation by taking some different mathematics. Trivial aspect of mathematics has been neglected here. So by, you can just remember that what is actually we got after doing some mathematical calculation, we obtained that cos k is equal to b sin alpha a by alpha a plus cos alpha a. Now this is the basic equation. We can just say that of the Schrodinger wave equation when it has been simplified with a particular solution with all the possible energies, and this can be, you can just see this, what is actually the meaning of p. P is nothing but 4 pi square ma v naught omega by h square. Now that is actually the value of P, and P is nothing but the scattering power of the potential barriers. It is Quervels when you say that is also known as potential barrier. So the potential barrier is mathematically given by this particular relation 4 pi square ma v naught omega by h bar square, and alpha is also given by 2 pi h by under root 2 me, where E is the energy which per permissible values, it will have a permissible values of -1 to +1. As V naught is increasing, the width of the barrier is decreasing, and V naught omega remains constant. We can just say that this is the what actually mathematical simplification which has been done with the solution, that is psi of x is equal to uk of x exponential of I kx, and instead of uk of x, we have just replaced uk of x plus a, and by all the mathematical calculation we obtain the equation cos k is equal to p sin alpha a by alpha a cos alpha a. So with this we can just say that this we studied in the lower class, in the previous classes. So okay, this has been studied, and what are the important conclusions we can draw by seeing this particular equation? What is actually the meaning of that particular equation in the physical sense? So according to Chronic and Pony, Penny model, they say that the movement of electrons in a periodic lattice is actually the how the movement of electrons is there inside the, what you can say, periodic lattice. Also, you just say that inside a metallic metal. So the electron movement will be looking like this. You can just see the schematic diagram, first schematic diagram. So in the first schematic diagram, you can just see that the movement of electrons in the periodic lattice is characterized by the allowed energy bands, and which are separated by forbidden region. You can just see this particular aspect. See the empty space is there, forbidden region, where you don't find any energy of the electron, minimum energy. And here, wherever you find that there is a waveform, that waveform is nothing but it gives, see, as the value of your alpha a increases, the width of the allowed energy band increases, and the width of the forbidden definitely decreases. Now what will happen when the potential barrier strength, that is P? We just studied about the potential barrier strength P, and what will happen to that potential barrier strength after doing all the mathematical calculation. So let us consider that if P is very large, or we can just say that P is large, then the function described on the right hand side equation, you can just see this function describes on the equation right hand side. When I say right hand side, you can just see that which is written as some exact value of you can see, you can see, I will show you. So what is that cos alpha a? On the right hand side you find the cos alpha a. So if the potential barrier strength P is large, then function described by the right hand side of the equation 1 definitely crosses. You can just see the waveform. This is this waveform, right? This is +1 minus wave, and this is crossing the value of +1. So thus the allowed band become narrower, and as you move to the move forward, so the allowed band becomes narrower, and the forbidden band become wider. So what will happen when the potential barrier is again it reached the maximum extended speed tends to infinity, the allowed is band will definitely reduce to a single energy level, and which will corresponding to the discrete energy of the isolated atom. So okay, now this is what we just started with the p value. So what is happening when P is equal to 0? Definitely you don't find any energy level exists and the particle is completely free. And thus, by varying the value of P from 0 to infinity, we can just say that the free electron, which has been assumed by the Root and Lawrence, can become completely bounded. You can just see the schematic diagram where the x-axis we just taken the alpha, on the y-axis we just taken P tends to 0. Now with this, we can just say this here the how these energy bands in the solids have been formed. This also we studied, but since it's a long gap, so we just will have very quick glance of this energy bands of solid. So when it is coming to the single atom, so we can just say this single atom has been single atom, you'll find that energy level is even. So what will happen to the two atoms? Definitely you'll find two energy levels, and three atoms you'll find three energy levels. If n atoms are there, definitely energy levels are. Now this is the case in order to understand very clearly what is actually the energy bands formation in the solid. We'll just have a very clear idea. So the band theory of solids, the energy band structure of the solid. So why we are actually studying this energy band structure or band theory of solid? We want to know the given element is either conductor or insulator or semiconductor. Now that is the reason that we are just studying about the energy band structure. So as you know that solid is containing enormous number of atoms which are closely packed with each other. Now this particular aspect you already know that since the atoms are closely packed with each other, so each atom with the isolated you can just say that if there is only one atom, you'll find that there is only one energy level. If there are n number of atoms, definitely n number of energy levels, and more energy will be accommodated in that particular what you can say more energy can be accommodated. So that is the reason that we say that so we just studied what happens to the energy level of the isolated atom as they are brought closer to the and also very close to form a solid. So if the atoms are brought in very close proximity, the valence electrons of the adjacent atoms interact. Hence, the valence electron constitute the or you can say single system of electrons common to the entire crystal. With this example, you can just see this what actually we have done. We have just taken you can just take up only one atom. Definitely that atom will have some energy level, and that energy level, so the if the number of atoms are increasing, definitely we just say that that is the reason that we say that therefore n electrons will have uh, definitely will occupy a different energy level. This is brought about by the electrical forces which are exerted in each electron by the nuclei. So the nuclei will exert some electrical forces to the electron. So and so we just say that as a result of these forces, the atomic energy levels split up into large number of closely spaced energy. Definitely, the set of such energy levels is said to be the energy bands of the solid. How this energy band is solid look like? You can see the very higher part. You'll find that valence band, and here there is a gap, and at last you'll find that there is a conduction band, and in between this conduction and the valence band, you'll find a very good gap. Right? We have taken this particular x-axis as inter nuclear distances. On the y-axis, we have just taken the energy of the electron. Particularly, we are talking about the electron. So the energy of the electron has been taken on the y-axis very seriously, and on the x-axis, we have just taken the internuclear distances. Now, this is actually in order to understand more clearly about the energy bands and the solid. What we have done is that we have just taken a very quick example of this energy level of a given atom. And why we have just taken sodium, definitely you'll find that there will be energy level of the sodium is become when the atoms are very close together, you can see that the interatomic distance between the atoms in a solid sodium definitely that will be varying. And when the atoms are in solid, they interact with each other, and the electrons have slightly a different energy. Now, this is a very, very important aspect with respect to the intermolecular, what you can say, distances. So the energy band, the allowed energies are almost continuous. We can just say that whatever the allowed energy bands are there, they are continuous, and also these energy bands are in general separated by a region, and we just had a very clear idea that this small space which has been left, so this region is known as forward and band, or we just say that is called energy gap. So the amount of splitting in is not the same for different levels, definitely not. So because the different what you can say, the elements will have a different energy level. So the levels filled with the valence electron in the atoms are disturbed to a larger extent, while those filled by the inner electrons are disturbed only less, or you can say only slightly, as you can just see in the figure. So if there are n number of atoms in a solid, there will be n allowed constant states. So you can just say that the atoms which have been formed the by means of the valence electrons, and simply we just say that is called valence band. And if this is the case, now these electrons have the highest energy, and above the valence band you'll find the next higher permitted energy band, which is called conduction band, and this conduction band correspond to the first excited state, and the electrons can move freely in this band, and we just say that is called conduction. One can just see this how, see, we had very clear discussion regarding the character of the crystal, and now we are just characterizing different elements. So when you just take the equilibrium spacing of the different elements right different elements, then on the x-axis you can see equilibrium spacing or not for different elements, and we just say that in the y-axis you have taken the energy. So as the you can just see that metal, semiconductor, and insulator. So the solid has been classified into these three categories depending upon the band theory of the solid. So here we need to again go for this. This is the basic mathematics. You can just see this, the type of mathematics what has been done, and at last we got this particular equation, right? So now when we just say this this particular aspect, see, you can I have just I want to show you how the different mathematical steps or mathematical calculations have been done in order to understand the basic significance of the Chronic and Penny model. So what we'll do is that in the next class, definitely we'll start up with the thermistor Hall effect, and also we just start with the semiconductor, the introduction to the semiconductor, the concept of hole. So in step wise, we'll just complete the chapter 1 very quickly. Then we'll move on to the chapter 2 of unit 2. And definitely this particular chapter is a very easy chapter when you just study it with with a little effort, will definitely give you more or fetch you more marks if you just concentrate on this particular what you can say particular topics which are there in the chapter 1. So it's a theoretical one, easily you can just remember it, right? So with unclear understanding. So when I say remember it, it is not only the mugging part what generally students do, but definitely you can understand this particular topic if you understand more clearly the concept. So it will be easy for you to reproduce in the examination, right? So you can just see this. This is what the waveform look like. So this is the how the conic penny model has demonstrated a simple one dimension. See, still now we whatever we studied and the two different when I say the Drude and Lawrence model also and the chronic penny model also, this is completely a one dimension aspect. You can just see the schematic diagram. This is also, you can see chronic penny say that they are square wells, right? And V of x here denote here the on the y-axis the potential of the particle, and that particle exactly we don't know. So if you don't know the exact particle, we just represent it with some x. So here also we have just represented that with the x. So that is called V of x, that is V of x is the potential of the given particle. What we are doing with this is how the potential is varying with respect to the different character of the crystal. That actually it has been shown schematically by means of this diagram, right? So with this, what we'll do is that we'll just stop our today's class, and in the tomorrow's class, we'll try to discuss about the what you can say thermistor, and also with the semiconductor. Probably we just start with the semiconductor, and you already know had the information regarding the semiconductor, right? So semiconductor, what is actually the meaning of conductor, semiconductor, and the insulator? As we just started with the energy bands of solids, by the energy bands of solid, we now conclude that the solids have been classified depending upon the band gap. They have been classified into uh, three different categories, that is conductors, semiconductors, and the insulators. So this particular aspect will be taught in a very clearly to you. So in tomorrow's class we'll just discuss about this the this conductor, semiconductor, and the insulator, right? So with this, we'll just take leave now, since it is a long class, which we just will have a very what you can say starting one of starting class. So we'll just conclude this today's class, right? And in tomorrow's class, we'll just discuss about the different topics of Unit 2, that is Chapter 1. With this, I will just take a leave for today's class. Thank you, everyone. Thank you for your patience. So, what we'll do is that we'll again meet on the next class, right? So we just say so. Okay, okay. Just thank you, everyone.